Thank you all for coming and for inviting Jacob and I to share our work with you tonight. Jacob and I first met through an exhibit that I had in 2012 at Boston's Sculptures Gallery titled Stuff Moves. Long story short, one thing led to another, and since January I've been an artist in residence in the physics department at Harvard. For the last 7 years, my work has been an exploration of movement, having a background in dance, martial arts, and now yoga. This was a concerted effort to merge my creative practice with my movement practice. Since then, my once static sculpture has become kinetic and interactive. Yes, it moves and you can touch it. As a result of the work becoming kinetic, I've taken an interest in physics, being that it is the study of matter and its motion through time and space. This statement explains. It's fascinating that there are predictable patterns in matter and motion. I'm interested in creating work that demonstrates this phenomena simply, with an aesthetic that allows the viewer easy access and provides a tangible way of seeing physics.
Hi everybody, I want to again also thank Kim, thank Deborah, thank you all for coming. As a physicist, I want to call your attention to the first of the two statements here. It's fascinating that there are predictable patterns in matter and motion. So when people ask me as a physicist, what is physics? Is it about particles? Is it about energy? Is it about mass? Does it have something to do with E equals mc squared? Is there a Higgs in there? What I tell them is that physics is all about, moving by itself. Use this one. Thank you. Yeah. Great. Learning how to use PowerPoint. Physics is all about patterns in nature, and in particular, the remarkable fact that the patterns that we see in nature, which we see all around us, appear to be derivable from a small set of rules that can be formulated in the language of mathematics. These rules, of course, are what we call the laws of physics. It's remarkable that this is true. When you read a fairy tale book, maybe to your children or when you were growing up, you know, these fairy tale worlds were filled with magic. There were no rules. They didn't need rules. They had a writer. But our world appears to have this strange property that there are patterns all over and they are explicable in terms of mathematically formulatable rules. And physics, if I were to summarize it, it's the study of those rules. It's the search for those rules, the attempt to understand them, test them, make sense of them, look for new ones. But they have a very significant significance. The existence of the rules means that the physical world, as complicated and messy as it looks, is actually a very redundant place. There's a lot less data out there than might at first meet the eye. With a relatively small amount of data and equipped with these rules, you can explain and predict a lot of stuff that's out there in the world. The rules of physics come in roughly 3 categories. Kinematics is what we call the rules that describe the state of things and how they can move. It's the what, and if you want, it's the where and the when also. Dynamics are the rules that allow us to predict the outcomes of things in physics, how things will change, how they will evolve, usually given information about the system state. And then larger rules, meta rules, like classical physics, which has something to do with what states there can be and what kinds of rules that we see around us. You've probably heard of Newton's second law, F equals ma. That's an example of a rule from classical physics. A different meta rule is quantum physics. Quantum physics is a more complicated set of rules that appears to govern nature at a more fundamental level, and we'll say something about it as we go. And these rules are kind of like the why. They give us an explanation and an understanding for the rules of kinematics and dynamics. And these will be themes that we'll come back to as we go through the work ahead of us. So now I want to call your attention to the second part of this statement, Kim's work and how it makes the story of physics, the patterns and the rules accessible to people who may not have a lot of background in it. So as we all know, art can be very beautiful. What may be less appreciated to maybe those who don't have the training is that physics can be very beautiful as well. And so it's very remarkable when someone can come along and bring out that beauty and make it accessible to people who might not otherwise be able to experience it.
This was the first of my kinetic sculptures. It's titled Bardo State, and it's an interactive kinetic sculpture consisting of 49 cement balls and 49 springs that are 3 feet long each. It's suspended from the ceiling. The cement balls were formed by hand in much the same way you'd make a snowball. Every 20 minutes or so, the cement balls need to be activated by a gallery attendant by pulling them straight down 1 foot. The Bardo state in Tibetan Buddhism is a meditational state or dream state lasting 49 days, occurring after death and before one's next life on earth. It's a restful state of quiet and reflection and regeneration after death and before rebirth, says the Tibetan Book of the Dead. I should share here that my son Kyle studied physics at Harvard and looks at my work often and offers input and feedback. When he saw this installation, Bardo State, he encouraged me to look up harmonic oscillation. This was the first time I had ever even wanted to revisit physics since my 10th grade physics class in high school with Mr. Ricker.
So as a physicist, I look at that art piece, I look at its motion, and what it evokes to me is the surprisingly fluctuating nature of the vacuum of space. When we think classically about empty space, it just seems empty. But one of the lessons of quantum theory is that empty space is actually frothing with fluctuating quantum particles appearing and disappearing, interacting with each other. What we think of as our placid macro reality is really kind of a washing out or averaging over all of these tiny little effects so that they're rendered almost unnoticeable. So I see those little bouncing balls, and I see this picture you see all the way on the left. This is a picture showing a fine-grain dynamical system. All those little rivulets are little variables popping around, kind of like the balls in that figure. And our classical world is what you get in that second picture, well, the picture next to the one all the way on the left, where we've smoothed or averaged out all of those details. We can't see them. And what we instead perceive is a nice, smooth, sensible reality. This is also depicted in the picture on the left. Sort of at the lowest level, you see spheres. You see spheres interacting in a dynamical way. And at higher levels, all those effects average out when we can't see them, and we see what looks like a simple, sensible reality. This has a profound impact in physics. Because of this difference or separation between what's going on at the very short distance scales, at the very small scales, these fluctuations, is somehow separated from what's going on at our everyday levels. And this separation of scales is actually the secret to why physics and all of science is possible. It meant that Isaac Newton didn't have to have a fundamental theory of nature before he could talk about balls rolling down slopes or planets going around the sun.
Having been encouraged to look at physics models, I started actively looking at physics demonstrations as a resource for sculptural ideas. This piece is titled Dance of Shive, and it's made of a nylon strip suspended between 2 columns with steel rods and 146 red bouncy balls. Since I had to order dozens of 6-color assortment packs to get enough red, I ended up with a lot of extra bouncy balls. Dance of Shive is named after Dr. John Shive, who developed a similar wave machine which invites the viewer to activate the piece by twisting the end to see wave reflection, standing waves, and resonance. I must say that I realize that I walk a thin line sometimes between my work being a simple demonstration of physics principles and being art. and I think about this often. That said, my considerations are first and foremost aesthetic, and I carefully determine the scale, context, materials, and the viewer's experience. Waveline consists of a 25-foot line of thin cables suspended from the ceiling. At the end of each cable is a 20-ounce lead sinker. The guys at New England Marine didn't know what to make of me when I went in and ordered 100 20-ounce lead sinkers. I got some raised eyebrows there. Unlike collision balls or Newton's cradle, the balls are connected horizontally. So they're hanging from the ceiling and they're connected horizontally as well. Wags either end of the line of balls, sending a wave of motion through the line.
Thank you. So I look at waves, and as a physicist, I see pictures like this. Both of these works, the Dance of Shive and then this amazing, what was it?
Wave line.
The wave line, right? Are of course wonderful demonstrations of wave phenomena. So Crash Course in Waves, right? We've all played with slinkies. You wave the slinky up and down and a wave goes by it. There's some names for stuff. Where it goes up, it's called a crest. Where it goes down, that's called a trough. The distance from a crest to a crest is called a wavelength. And waves, when two waves meet, if they meet where crest meets a crest, they add together. That's called constructive interference. That's the first figure you see over there. When a crest meets a trough, or a trough meets a crest, they cancel, and that's called destructive interference. When you send a wave down a line, like the Dance of Shive, and the wave comes back at you, the wave that reflects back can interfere with the wave you sent. And this can produce beautiful, what are called standing wave patterns. You may have noticed in the Dance of Shive that a wave seemed to be traveling, and then after a while, it didn't seem like anything was moving to the left or right. Things just seemed to be going up and down. That's this phenomenon of standing waves, where certain points of destructive interference, called nodes, are those spots there where there's no motion, where the intersections between those lines. And the up and downs, those are where there's constructive interference. The waves have added together.
Ready-made color wheel explores perpetual motion, which of course doesn't exist, and color mixing with a nod to Marcel Duchamp and the subversive playfulness in his work. The viewer is invited to give the bicycle wheel a spin and watch the balls perpetuate their own motion, and sometimes reverse direction. This is an example of coupling, where the movement of each ball affects the others.
Thanks. Yeah, and so when I look at this, I see in particular this phenomenon of nonlinear coupling, where what the system is currently doing can affect the rules that govern how the system will behave. And this leads to a phenomenon called chaos. So, all right, again, crash course. The slinky example is an example of a linear system, a system where what comes out, the rules, are very predictable. If you change how high you raise the slinky just a little bit, what comes out, the outcomes, will also change just a little bit. The behavior is nice and easy to predict. In this example, we've doubled how high we're lifting it, and the result is a wave that's twice as high. But for a system that can feed back on itself, a system whose current state can affect its own dynamics, is called nonlinear coupling or feedback. You get very unpredictable behavior. In fact, the behavior is called chaos or chaotic dynamics. There are two visual depictions of chaos here. These are the kinds of depictions physicists often use. The figure on the left represents a particle. The horizontal direction, the horizontal axis, is where the particle is. The vertical axis is how fast it's moving. And each point in that figure on the left is a state of being for the particle, where it is and how fast it's moving. If you put the particle at one spot on that diagram, it means you're putting it in a certain position at a certain speed and letting it go. And you'll see that at certain points, you get these beautiful orbits, where the particle, after a very brief amount of time, returns to its original state. But then if you put it at slightly different points, you'll notice you get fuzz. That fuzz is chaos, where slight changes to where you start the particle lead to dramatic changes in where it ends up. This is also illustrated by this diagram over here. This is a mathematical representation of what's called the logistic map. Basically, it's just another dynamical rule. And what this depicts, the vertical axis is where the system ends up. Okay? The horizontal axis is basically a parameter you can tune to decide how much feedback there is in the system. When there's very little feedback, then regardless of where you start the system, it ends up in the same state. That's why you see one line. As you tune the feedback parameter more strongly, eventually the line bifurcates into two lines. And that means that slight changes to where you start the system can lead to one possible outcome or the other. And as we increase the feedback parameter, we get this amazing fractal structure, where the system's final state depends extremely sensitively on where you start it. This is a wonderful example of chaos. Kim's work reminded me of a piece at the City of Science and Industry. It's a wonderful science museum in Paris. It's called the turbulence clock, and it consists of a wheel inclined slightly into the screen. It's inclined at about 45 degrees. What you can see at the very top is a fountain. Water is pouring into the funnel at the very top. These are all funnels, and the wheel can turn. But the funnels have holes in the bottom. They leak water. As water pours into the funnels, gravity pulls the funnels down and causes the wheel to turn. And as the wheel speeds up, the funnels fill with less water. And so the system eventually stops turning so fast. But then it slows down and begins to fill with water, and then it turns faster. And you get a dynamical nonlinear coupling that leads to unpredictable behavior. The wheel will change direction and do all kinds of funny motions.
This piece is titled Quantum Revival, but it could have just as easily been called Pendulum Wave. It's an installation of 15 red balls hanging from cables of increasing length from left to right. They are not coupled. They are independent of one another. When let loose, the balls leave the chute at the same time. Since the carefully measured cable lengths increase formulaically, the period creates a choreographed wave dance. You probably want to see that, don't you? These uncoupled, simple pendula synchronize themselves to produce visual traveling, beating, and standing waves. So if the video went longer, you would see that it would cycle back around again and repeat that whole choreographed movement.
Yeah, you almost saw it in that last moment when there were two waves, if you waited long enough, exactly.
Some like this piece best seen from below.
So this piece is a beautiful illustration of a phenomenon known as Poincare recurrence. This goes back to a theorem proved by Henri Poincare. He was a mathematician and theoretical physicist. He published a paper in 1890 arguing that with certain assumptions about the dynamics of a system, in particular that the particles can't go as far as forever, that eventually a system, given enough time, a finite amount of time, not infinite time, finite amount of time, will return to a configuration or a state that is very similar, close to, if not exactly the same as where it started. And it will do this infinitely many times. And here we actually see a visual representation. That's Henri right there in the upper corner. And there's a rule for taking that initial picture and changing it in a prescribed way at each step. And actually this is compressed. The first few steps are shown, and then it's 1847, 237. But by 241, the picture has returned almost to exactly where it started.
Why 241?
It's a good question. It depends on the nature of a dynamical rule. For a very simple rule, you might return to your initial state right away. For a more complicated rule, it might take more time, but eventually you get back there. For the particular rule that was being used here, it was 241 steps. Now, see that one moment there where there was a peak in the middle? This is a mathematical representation of a particle put into a two-dimensional trap, a flat trap. The horizontal directions are how far the particle can move. The vertical direction is not a real direction. The vertical direction is telling you how likely it is to find the particle at a certain spot. When the particle began, it was very likely to be found in the center of this trap. As time goes by, because in quantum theory, particles are described by probability waves that can interfere and reflect and bounce, the particle undergoes standing wave patterns and eventually a full recurrence, in this context called a quantum revival, and returns to where it started. You're made of those. Yeah.
This is titled Hydrogen Atomic Orbitals, and it came about as a result of Googling quantum mechanics. I was trying to wrap my brain around what quantum mechanics is, and I can't explain what it is today, of course, but what I did learn is that electrons in matter follow an orderly natural system. These clusters, where the balls are most dense, show where the electron in the atom is most likely to be found. This project required that I rolled thousands of clay balls, which I did while my husband and I drove from Maine to Key West and back. So by day, I would sit in the passenger's seat and I would roll balls. And at night, we would stay in a hotel room and I'd lay them out on a table to dry.
If you want, I can explain quantum mechanics. It's just like classical probability theory.
Short version.
But it's not commutative. OK, yeah. So these are mathematical simulations of the different states, the different ways that an electron can be as it goes around a proton. And what you get when you have one electron, one proton, is a hydrogen atom. If you were to imagine exciting the electron, making it a little more excited, then the shape of that cloud of probability, the shape of where you're likely to find it, changes. And what you see here depicted are various excited configurations or excited states of that electron around the atom. In the first one, the lowest excited state, or the ground state, the electron has a spherical probability cloud. It's equally likely to be found sort of anywhere rotationally around the center of the atom. And in the more excited ones, you see very non-trivial geometric shapes for its probability cloud. In particular, Kim's figures closely correspond to 3s, 3p. Those are the two ones in the upper right, and 3d over there near the bottom. And these clouds, in the case of a hydrogen atom, are called orbitals. So that picture you've probably seen of the radiation atom with those sort of planetary orbits, that's not a very accurate picture. This is more what the correct picture looks like.
This brings us to my current exhibit titled It's Physical at Suffolk University. It's currently on view until October 3rd, which is Saturday. This exhibit features my newest work, which I've created since being the artist. A line of springs and balls. On the back, there's a grid of springs and balls. The cube in the corner on the right, balls and springs again. The two paintings on the wall are polyhedrons. And there are a number of pieces on pedestals and on the walls that are hyperbolic surfaces. 50 Springs is a collaborative project between myself and Rob Hart from Harvard. Rob's right here in the third row. The wrap balls were made out of recycled bicycle inner tubes, which allowed us to make each ball a different mass. And by using long linguine and spaghetti strips of shredded inner tubes, determine the weight of each ball to the fraction of a gram. With the idea of creating a bouncing piece that did not require a gallery attendant or a viewer to activate, we used a motor to drive the 50 balls at 50 different, and there are 50 different weights, masses, driven at 88 different frequencies over the course of a 12-minute loop. So the resonance moves from, let me start the video for you and I'll point it out. The resonant frequency moves along the line of springs and balls. So you could see where the amplitude is the greatest, where it's bouncing the highest. That's where there's a resonant frequency, but that point moves up and down along the line of balls because the frequency changes. So the frequency finds masses at different points along the line, and you'll see it's most resonant where it's highest and lowest bouncing, and then the balls that are bouncing the least are deconstructive. Yes? Yes?
I like that.
Okay.
I just wanted to say quickly a wonderful Rob Hart story. He's a truly amazing person in our department who loves oscillators. We had an undergraduate once ask me in Rob's presence what the meaning of life was. And Rob's response was, I don't know, but I think it has something to do with harmonic oscillators. It's great. By the way, I want to point out that Kim's piece, in addition to being remarkable and beautiful to look at, also demonstrates a very important idea, which is that you can determine the mass of a ball in that display by what frequency it goes into resonance. This is an important idea we'll be coming back to because it plays a very deep role in the cutting edge of modern particle physics. But let me say a little something about resonance. So this is a graphical depiction of what physicists mean by resonance. Take that slinky or take pushing a child on a swing. You probably know that if you time your swings, you time the force you're putting into the system just right, then you get constructive interference. You keep adding to the strength of the oscillation, what we call the amplitude, and eventually you can build up a very strong amplitude. This is a depiction of putting in different rates of pushing, and how if you pick exactly the right frequency of pushing, you get a spike in how strong the amplitude is. It doesn't go infinitely tall because of friction, otherwise your child would launch off of the swing into the stratosphere. But of course, there are lots of examples. I mentioned the swing example. Another example you're probably all familiar with is the example of the opera singer who sings at just the right pitch, which corresponds to a sound vibration in the air that causes the glass to vibrate at just the correct frequency where you get constructive buildup interference and it causes the glass to shatter. You probably also know that resonance shows up frequently in musical instruments. This is, in fact, how musical instruments produce their characteristic sounds. Here we have a graphical depiction of a guitar tuned to 110 hertz. A hertz is 1 oscillation per second. And so we see here that when you put a vibration on the string that's 110 hertz or any integer multiple of 110 hertz, 220 hertz, 330 hertz, you get resonance, an increase in the volume of the sound, which is the strength of oscillation in this case. What does this have to do with particle physics? I mentioned cutting edge physics. Well, back in the old days, if you were looking for particles, you would look for them with your eyes. You'd build what's called a bubble chamber or a cloud chamber. In fact, Rob knows how to do this. I believe Rob knows how to do this. I don't. I'm a theoretical physicist, so I don't know how to do this. But what you would actually see is little streaks of bubbles or mist as charged particles moving through a supersaturated solution leave a trail as they ionize particles in the solution. And here in this picture on the right, you see a really beautiful depiction of trails left by various particles. They're even labeled. You can see a low-energy electron, a proton with a delta ray, the delta ray coming off of it, an alpha particle, high-energy electrons. We don't find particles this way anymore. We don't find particles this way anymore because now there's so many elementary particles, and their interactions are so messy, and the ones we're looking for live such a short period of time that we just won't ever see them. They live such a tiny fraction of a second. So instead, we look for them using resonance. We look for them and determine what their mass is using resonance, very much in the spirit of what Kim was doing. If we think there's a certain kind of particle and we know what stuff comes out when it decays, well, what we do is we collide particles together in a big atom smasher. You probably heard of the atom smasher in Europe, this giant ring. We collide particles together using a lot of energy, and by E equals mc squared, we produce ideally the particle we're looking for at its mass, and then it immediately decays. We count up all the stuff that comes out when it decays, and we build up a chart, a histogram that counts how much stuff comes out as we collide things together with different energies. And when we have just the right energy, that we produce just the right mass for the particle we're looking, we get an overabundance of decay products that shows up as a resonance. This is a beautiful resonance showing the discovery of what's called the lambda meson. You can see its mass right there on the chart is about 5.6. The units we use, the measurement units, are kind of funny. They're GeVs per c squared. Don't worry about that. The Standard Model is our best model of fundamental interactions of nature. It's been experimentally confirmed. It is the most precise and well-tested model in the entire history of humankind. And it consists at the kinematical level, that is the what. It consists of a menu of different kinds of species of particles that describe matter. That's the quarks and leptons. The electron is a kind of a lepton. Protons and neutrons are made of quarks. And then things that carry forces. The photon is the most familiar. It carries electric and magnetic forces. There are other force carriers as well. And the famous Higgs. At the level of dynamics, the rules that govern what comes out when you smash particles together, the rules that govern how they interact with each other, the rules can be summarized on a mug. That L you see at the beginning there is called Lagrangian, and it's a way of compactly representing the dynamical rules of the Standard Model. But it's very complicated. Now, the capstone of the Standard Model, the particle that took the longest time to find, was the Higgs boson, that plays a very important role in giving intrinsic masses to the quarks and leptons. It's very important. Without it, the electron would have no mass. It would fly out of all of your atoms, and you'd cease to be. It would be unpleasant. Now, to find the Higgs, it took a lot of work. But you can see in these three figures that were well publicized after it was found in July of 2012. Well, it was found before that, but it was announced in July of 2012. You can see beautiful resonances. If you look at the charts, the first chart, the light blue resonance, the second chart, the red line, and the third chart, that red lump over there, all at about 125. And the units, again, are GeVs per c squared. And these were the results of work done by the ATLAS and CMS groups. And the announcement was made on July 4th. So in addition to being Independence Day, physicists often think of that as Higgs Day. But I want to emphasize again this idea of looking for particles and determining their masses by looking for resonance, very much in the spirit of Kim's work.
All right, let's change things up a little bit. I travel between Cambridge and Rockland, Maine weekly, and I frequently stop at bicycle repair shops, and I've gotten a number of them to hold on to their bicycle inner tubes from flat repairs. So I decided to see how big I could make a sphere out of the leftover inner tubes. This sphere is made out of 119 inner tubes, and it's perhaps still growing. You've probably noticed that I use balls and spheres often in my sculpture. I can't imagine a more perfect shape. It's flawlessly round and symmetrical, an ideal geometrical object.
Leave that slide up for a second. So how many of you, I guess you don't have to raise your hands, but how many of you, you were in school and you referred to this as a ball, and some teacher or some pedantic friend's like, no, mathematicians call that a sphere, right? You probably heard this before. Well, I'm here to tell you that you were right. Technically, the outer two-dimensional surface, the surface of this thing, is what mathematicians call a sphere. Sometimes they call it a two-sphere to really emphasize the 2D flat aspect of it. The three-dimensional object, the actual three-dimensional physical object that surface surrounds, that's called a ball. Mathematicians call it a ball. So you were right. Okay. Now, spheres and balls play a very important role in physics, both as actual physical systems that we see, but also as mathematical tools for better understanding what's going on in physical problems. Soap bubbles, in particular, have a long history in physics. The importance of spheres at a metaphysical level goes way back. The ancients believed that all the celestial objects, stars, planets, the sun, the moon, were fixed to a giant dome in the sky. This is, if you read Genesis and it talks about God creating the firmament, that's what they were referring to, a giant dome, which is what they thought that the sky was. This idea gave way to the notion of celestial spheres surrounding the Earth, with the Earth at the center of the universe. This was the Ptolemaic idea, and all the planets and stars and so forth orbiting around the Earth. This idea had obvious problems. The planets undergo loop-de-loops in the sky, and this was accounted for by putting sort of cycles or epicycles on top of the spheres. The model became very complicated. So although we've abandoned that model, the idea of a celestial sphere survives in various kinds of senses. And one in particular is really a very, very wonderful and marvelous sense. So you've probably all heard of the Big Bang model. This is the idea you look out at the universe and you see faraway galaxies speeding away from us. Well, if you run that clock backward, at some time in the past, the calculation right now is 13.78 billion years. We're down to 2 decimal places. The universe was very small and very, very, very hot. So small that all the parts that we can currently see fit into a region smaller than an atom. The universe, for reasons not totally understood today, began to expand. As it expanded, it cooled, but it was still very, very, very hot. And in fact, for the first 380,000 years of the universe's existence, it was so hot that there were no stable neutral atoms. There were electrons zipping around and protons. And light bounces or scatters off of these things. It cannot travel very far. So the universe, if you could look at it, was a bright, opaque volume. And years after the Big Bang, the universe had expanded and cooled just enough that electrons joined with protons and formed stable atoms, neutral atoms. Neutral atoms, light can pass through that. And for the first time, the universe became transparent. And the light that escaped at that moment has been traveling through the universe ever since. It's called the background radiation. And it's not all exactly the same. Some of it is a little redder or a little greener. The light's not all exact same color. And the different looks of the light actually capture fossilized imprints of what the early universe looked like. When we look out at the universe, you probably heard that we're seeing back in time. We're seeing things as they looked longer ago because it's taken light time to reach us. There's a wall to how far we can see. If we look back at the universe all the way far enough that we're seeing it as it was 380,000 years after the Big Bang, the universe was opaque to light and we can't see any farther. It's as if any person standing in the universe, in any galaxy looking far enough out, would be surrounded by a giant opaque sphere. The Big Bang Theory predicts that sphere is there. It's not really a sphere, but it's light coming at us from that early phase, bearing in it fossilized imprints of what the universe looked like in the early days. It's a prediction of the Big Bang model that was experimentally observed by accident in the 60s by Penzias and Wilson, who won the Nobel Prize for it. We now study those fossilized imprints. You can see that in that picture taken by a famous satellite, the WMAP satellite. And in particular, I want to draw your attention to this picture over way on the right. That picture shows how the wavelength of that radiation, which is mostly now, it's cooled, it's now microwave radiation, so it's called the microwave background, how the frequency or the color of that radiation, how that compares to how bright it is. And if you plot the dots you see on that picture, you can barely see error bars there because the experiments are so precise. The dots are taken from measurement, and the solid line is the theoretical prediction. The Big Bang model predicts that solid line, and the experiments match it perfectly. It's one of the most beautiful matches between experiment and theory. I'll say something very briefly about approximations we use in physics. This is the so-called spherical cow approximation. It's a metaphor for the sort of coarse approximations we often use in physics that work very well. It works very well in the solar system because the solar system consists of planets that are round. And this was very important in the early development of physics because it meant that Newton could formulate laws of gravity that worked not just for point particles, but for the spheres in our solar system.
This is a piece that I've been wanting to create for years. It's titled Quiver, and it's a grid of springs and balls, and the balls are made out of, again, recycled bicycle inner tubes. The viewer taps a ball and the entire grid quivers. To let viewers know which sculptures they can touch in the gallery and which they cannot, we used icon graphics next to the labels on the gallery walls. I try to as often as possible, allow the viewer to touch the sculpture, to activate its motion, and to have a tactile and multisensory experience whenever possible. In the basement of the Harvard Science Center, there's a storage area where Lecture Demonstration Services keeps these wonderful models that are brought out when professors want to demonstrate for a class. This kinetic sculpture was 100% inspired by a ball and spring model. It's titled Phonon, and it invites the viewer to give it a whack and see its motion.
Thanks. So this is a graphical depiction of that ball and springs model. It's again one of the unjustified but frequently very successful idealized approximations that we use in physics. In particular, it's very useful for describing the atomic lattices that make up solid matter. This is an illustration, figure 1.1.1 of a very popular textbook on quantum field theory. And you notice it bears a striking resemblance to one of those early works. This is how physicists think about systems called fields. So what's a field? A field is a physical system distributed in space that you can excite and you can send waves through it. At a quantum level, it turns out that you can only excite it at the smallest in little discrete quantized amounts. That is, there's nothing, or if you excite it the smallest possible amount, there's one quantized excitation that can travel. And we actually interpret those little quantum excitations as particles, the particle that corresponds to that field. The electromagnetic field has a corresponding quantized particle that we call the photon. The Higgs field has a quantized particle that we call the Higgs boson, and that's how these are related to each other. And this is another graphical depiction of a similar kind of a system. This represents an atomic lattice. And here, what we're showing is each of the atoms that make up the lattice vibrating slightly around their equilibrium position. The small quantized excitations of this system are called phonons, in analogy with photons, because phonons are kind of like the small discrete vibrations that correspond to sound. And that's the inspiration for the name for the phonon piece that Kim was describing. Phonons play a very important role in very important basic physics. You probably know that electrons are negative. Negative charges push against each other. When an electron is traveling through a metal, which is described by a lattice as well, a lattice of positive charges, those are the big spheres. The electron is the little one. The electron tugs on the positive spheres, brings them together and forms a positive region that can attract other electrons. That means electrons can actually pair up in a metal. And at very, very low temperatures, they can pair up into pairs and coalesce into a quantum fluid that leads to a phenomenon called superconductivity. Among its many applications, it leads to things like magnetic levitation that's used in various applications.
Also in the exhibit is this 8-foot wide painting, which is titled Icosahedron, which is what it is a template for. When 20 triangles are folded together, it creates a polyhedron. Dodecahedron is also about 50 feet wide, 8 feet wide. Not 50. Maybe the next one.
The attack of the 50-foot dodecahedron.
And it's composed of 12 pentagons that when folded also create a polyhedron. The surface has crisscross lines that echo the texture of the wrapped inner tube balls throughout the exhibit.
These are both examples of platonic solids. There are exactly 5 platonic solids, a fact that's been known for thousands of years. A platonic solid, briefly summarized, is a 3D shape you get by combining identical 2D shapes that are all equilateral, equal-sided. And you can see here there are just 5 of them. And there are only 5 because the purple one is called a tetrahedron. It's made of 4 shapes. It's what you get when you attach 3 triangles at every corner. The octahedron, the yellow one, you get by attaching 4 triangles at every corner. The icosahedron, that's 20 sides, that's the blue one. That's what you get from attaching 5 triangles at every corner. And you can't do any more. If you attach 6 at every corner, you get a flat shape that can't make a 3D shape. If you attach squares together, you find you can only attach 3 at every corner. That leads to a cube. 4 squares at a corner is flat again, doesn't lead to a shape. And finally, if you take pentagons, that's the 5-sided shape, and attach them, you see you can only fit 3 of them at a corner. That leads to a 12-sided dodecahedron. And again, you can't fit any more than that. If you try to use a hexagon, you all know from looking at beehives, hexagons fit to make something flat. So that doesn't work either. And that's why there's only 5 platonic solids. My daughter asked me why when you add the numbers of their sides together, you get 50. If you add those all up, I don't know the answer to that question. If you slice the edges of platonic solids just right, you can unfold them and you get what are called nets. And you'll see that the green net and the red net closely correspond to what Kim has described. There's a deep question in mathematics. If you have any polyhedron, any 3D shape, or maybe the sides are not all the same, is it always possible to slice them and unfold them in a way you get one connected piece called a net? It seems intuitively clear that should work, and every time it's been tried, it's worked, but it's not been proved. It's a conjecture that dates back to 1975 called the Currier conjecture. Plato was so fascinated by the Platonic solids that about 100 years after Democritus first proposed the idea that all matter was made of atoms, Plato wrote a set of dialogues called the Timaeus, in which he argued that all of the four known elements of nature, fire, wind, earth, and water, were made of little tiny atomic Platonic solids, too small to see. And moreover, the sharpness or hotness of fire was related to the pointiness of the tetrahedrons that made them up. The solidness of earth was the cube shapes of the earth. There was a fifth solid that didn't correspond to a known element, so he proposed a fifth element, which he took the universe. Interestingly, the Standard Model's got four forces, plus the Higgs, the fifth force. Is that important? You decide. Kepler, who you might know is the one who figured out the elliptical shapes of the orbits, proposed that the Platonic solids could explain why there were 6 planets. He imagined there were 6 spheres the planets lived on, this time centered around the sun, which is more correct than the Ptolemaic model. And the reason there were 6 spheres is because that's how you could describe spheres between 5 Platonic solids. He even thought you could explain how far the planets were from the sun in this picture.
The next few sculptures are crocheted out of what other than recycled bicycle inner tubes. This is a hyperbolic skirt. A hyperbolic plane has more surface than is required for a two-dimensional flat surface, and it begins to fold and ripple as the surface expands. This occurs in nature in kale, seaweed, and coral. If you think of hyper meaning excited and bolic meaning bowl, it basically means it's an excited bowl. In crochet, you build up by going around the form 1 stitch at a time. When extra stitches are added beyond what is needed to make a flat surface, the circumference expands exponentially. Some of you may be familiar with the Coral Reef Project, which was inspired by Dr. Dana Taima, a mathematician from Cornell. In 1997, Dr. Taima discovered how to make models of the geometry known as hyperbolic space using the method of crochet. Like those contributing to the Coral Reef Project, I too was inspired to create these hyperbolic forms in various iterations.
You see here a beautiful depiction of coral and the close correspondence of its shape to the art that Kim was creating.
Makerspace, where visitors can try their hand at hyperbolic crochet in a hands-on activity. Yeah, we're short on time, so I'll go through this quick. Non-Euclidean geometry is pretty simple, right? We don't have to spend too much time on it. You probably know that on a flat plane, 2 lines initially parallel stay parallel forever. A triangle, if you add up all the angles, is 180 degrees. If you divide the circumference of a circle by its diameter, you get pi, 3.14. Well, these rules don't hold on a curvy surface. On a surface of positive curvature, like a sphere, the circumference is too small compared to its diameter, and the ratio is not pi. The sum of angles of a triangle can exceed 180 degrees. And parallel lines, initially parallel lines, can converge, just like the 2 parallel lines at the equator will converge as they meet at the North Pole on the Earth. Kim's work actually corresponds more closely to hyperbolic surfaces, where those rules are all reversed. Now, hyperbolic space extends infinitely far. If you want to visualize it on a 2D plane, you have to do something clever, like M.C. Escher did. M.C. Escher here is visualizing a tiling pattern of angels and demons depicted on a hyperbolic surface. He's picked a random point as his center, and as he's moved away from the center, he's shrunk the distance, the sizes of everything, so he can fit infinity in a finite size. This isn't just nice art or even nice mathematics. Physicists use exactly this way of thinking to take the shape of space-time from Einstein's theory of gravity and depict it on paper. A question that's existed since Einstein proposed that gravity causes its effects by warping the shape of space-time is if you look across the universe at very, very big distances, much larger than stars or planets, does the overall shape of the universe have a curvature to it? If you could imagine creating a giant triangle with the sum of the angles be 180 degrees. Turns out the answer depends on how much matter there is in the universe, how much stuff there is in the universe, and remarkably, experiments done famously in 2000, the boomerang experiment, showed that we're apparently in the 3rd scenario with a universe that on large scales is approximately flat. I'd say that just about wraps it up.
conversing for this whole time. We have a short amount of time, and they'll be up here, and if anyone has a comment or question, it'd be great. Actually, I'll start.
You're on the microphone.
Yeah, I guess. Thank you. So, thank you very much for that. I know you did a lot of preparation to have this kind of back and forth conversation, and I thought there was just a tremendous amount of clarity visually and sort of intellectually from both of you, so it was great. And I just want to comment that the 50 Springs piece that's in the exhibition, almost to a person, people ask me, oh, was that like, is there an algorithm for that? Was that like, is it computer generated? And it's a really mesmerizing piece, Rob.
Mm-hmm.
And anyway, it's just been really, kind of satisfying to sort of see it on an almost daily basis and know that it's like based on physics and it's what's happening in sort of real time in real space.
So this was a collaboration between Rob Hart and myself.
Yeah.
So Rob was the one that masterminded the motor and the little programmer and figured out the different frequencies, and we did make decisions on how it would move. Initially, the line of balls was going to make this kind of motion. So we were going to, the reason that we decided to use inner tubes is because we could really determine the mass by adding more length or reducing it to match the masses with the frequencies that we wanted. So I have to give a lot of credit to Rob for figuring out the physics of it. I'm good at wrapping balls, though.
That was lovely. Very well integrated, which is terrific. So a trivial question, the decision to make everything black in your show,
Yeah.
you can answer that quickly, but the deeper question is, the work beautifully demonstrates kinematics. Have you thought of much about trying to, illustrate, explore the strangeness of quantum mechanics, which is a concept that, I'd love to see you
Yeah.
take the same energy you've done with kinematics to take something that's much harder, I think, for the average person to
Right.
to
Yeah,
visualize.
it has to be something visual that sparks my interest. So I need to be able to see that there's visual potential in order to have an idea to work with. If it is so elusive that I can't drum up an image in my mind when it's explained to me, then it's very difficult to think about how this can be a sculpture. To answer your question about the color or lack of color, it was a very conscientious decision. I really wanted it to not be, much of my work is very colorful. With this show, I just wanted it to be black, white, gray. It just seemed to lend itself to the space in the exhibit. It's not a huge gallery space, but I also wanted it to speak to the seriousness of the work and that it does move, but it's not playful in the way that the color wheel was.
I apologize ahead of time. I was trying to figure out what you were doing here, other than responding to some of the work or a lot of the work that's gone on in theoretical physics and representing it and illustrating it, etc. But where was Kim in all of this? I guess what I didn't get, and I again apologize, is the sense of you as an artist. In addition to doing the rubber stuff and hanging these things in resonances, I didn't understand that, frankly. It was in a way as if you were illustrating a textbook, as opposed to doing your work as an artist, sort of transforming the inputs you were getting from physics into something that would explode, beyond, again, an illustration of what you were talking about. This is probably totally incoherent, but I was getting frustrated. Where the hell are you in all of this?
Well, I mean, my work is not about me.
Well,
But
it's
it-
not about you, but you are the one who was doing it.
Right. And because I am fascinated by movement, and because I have a background in movement, the work is about movement. And that's my primary interest. So that's where the interest in physics has come from. It's not because I'm trying to demonstrate something for a physics class, or to, I do appreciate that through the work, someone can understand more about movement and can have a basic understanding of some physics principle. But it's essentially the movement that I'm really interested in. And I think I addressed what you were addressing when I was speaking, and I do think often about what makes this art and not a physics demonstration. Where does it differ? And I see that with models that demonstrate physics principles, which there's hundreds of in the Science Center that they bring out to display for a class, the model takes no consideration of aesthetics. Its function is to demonstrate a principle, period. It can be made out of simple materials. It can be small. It doesn't relate to its context whatsoever. And it has no aesthetic considerations. It just has to perform its job. So I see that in order for something to transcend into the realm of art, then the context has to be considered. The viewer's experience has to be considered. The materials have to be considered. The color has to be considered. I mean, there are all these aesthetic considerations that I don't see someone who builds physics models has to contend with.
If I just add, as a physicist, I look at Kim's work and I don't see physics demonstrations. What I see first and foremost is art. To the extent that physics plays a role in Kim's work, I see it the way that a painter uses colors. Kim uses physics as part of her palette to create things that might be difficult to create or express in other ways. When I look, for example, at Bardo State, that was that first piece that Kim showed with the balls hanging off of the ceiling, bouncing around, and also 50 Springs, which is somewhat of a similar idea. I don't see physics first and foremost. I see the expression of ideas and feelings, but using the tools of physics to provoke the viewer in a way that might be difficult to do with a static piece of art.
Hello. I have to say how much I enjoyed both of your presentations, and there was a beautiful marriage between both of what you presented. But I would agree and respectfully disagree with the other gentleman's comment that I'm surprised that the word aesthetic did not immediately jump out to him, because I really felt it was an aesthetic education. There definitely was the influence to learn what might be happening kinetically and in movement, but I think it was all art, Kim, what you did, and I just was really taken with everything.
Thank you.
I think we have time for one more question. Anybody has a question or comment?
Thank you both very much. I have a question for both of you. The word beautiful has been talked about a lot, and I think that the way that artists define beauty and the way that physicists define beauty is perhaps different. So I'm wondering how you see beauty and what the value of beauty is. Why is it something that we should want in our lives?
You want to take that first?
I'm going first.
I'll take that question.
Yeah, you use beauty, Jacob.
I'll take that question. I don't have a good definition of beauty. I don't have a good definition of love either, but I know love when I feel it. People attempt to define what love is, and whenever they do that, they do an injustice to what it really means. You can't explain it, you just know it when you feel it. When I see something beautiful, I have a certain feeling that I associate with that. And I have the same feeling whether I'm looking at a really, really beautiful piece of art as I do if I'm looking at a very elegant equation, or when I learn a sublime physical concept or mathematical concept. To the extent that you believe what's coming out of fMRI machines, and there's reason to be skeptical, there's some evidence that when mathematicians and physicists look at a really sublimely beautiful or simple equation, that there's activation in parts of their brain similar to when someone looks at a beautiful work of art. When people say that physicists see something differently when they see beauty, I think, again, that's just a matter of maybe not having the training to perceive the beauty that's inherent in physics. The way that maybe someone who becomes very well versed in a certain musical instrument can detect kinds of beauty that might not be available to somebody who doesn't know about it.
Good.